Hi everybody. Today we're going to talk about section 3.8 in your book, and it's derivatives of inverse trig functions. So if you don't remember, that's your arc sine, your arc cosine, your arc tangent. And we're going to do a quick algebra 2 review. There's two things, A and B lettered here, that we need to review. And one is, if you could please real quick try to find the arc sine of 1. I'll give you, you can pause me, take your best guess. I find that students do struggle a bit with this because we don't spend a lot of time on them in trig and our trig work and in our algebra 2 and pre-cal, and we don't spend a lot of time on them in calculus either, but we should be aware of them, especially arc sine, arc tan. Okay, so y is the angle. That's what this means. And you see arc, that idea that the central angle is the same as the arc length on the unit circle is important. So when you read this, this is y is the angle whose sine is equal to 1. And hopefully we know which angle has a sine of 1. So we'll take a second here, and I'll give you one that you can work on your own. There we go. All right, go ahead and answer that one. And hopefully we ended up with pi over 4. Okay, the second thing that we need to be familiar with to be okay with this section is what I call the big duh of trig. I know that's not really very professional, but this is the idea that the sine squared of any angle plus the cosine squared of that same angle, no matter what it is equal to 1. And there are two more. One of them we can get by dividing both sides by cosine, or both sides here by cosine. So sine divided by cosine, cosine squared gives us tangent squared. Cosine squared divided by cosine squared is 1, and 1 divided by cosine squared is our secant squared. And then the other one comes from dividing both sides from the original big duh of trig up there by sine. So sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. And 1 over sine squared is cosecant squared. And those are our three Pythagorean identities. Really, the first two are the only ones we're going to use in this lesson. All right, so let's talk about derivatives of inverse trig functions. Hey, what's the derivative of arc sine? Well, if I knew, we wouldn't be doing this lecture. So I have no clue what the derivative of arc sine is at this point. So let's use some of our strategies to figure it out, and then we'll never have to do this again. We'll just memorize it, right? We'll just remember what it is. Okay, so arc sine, okay. So what we want to look at here, I'm going to rewrite it just a little bit. Let's say that that's our function y, and we're supposed to find the derivative. We can't because we just don't know this derivative pattern yet. So we're going to change forms much as we did in the examples 1 and 2 up above. So we're going to say if y is the angle whose sine is x, then the sine of y must be x, right? We can just change forms. And now we're looking really good, because you may not know that yet, but we are looking good because I do know I can take the derivative of this with respect to x. I know that the derivative of x with respect to x is 1, and this is our implicit differentiation lesson from 3.7 coming into play today. And I know the derivative of sine is cosine with the inner function unchanged times the derivative of the inner function. And now I can just solve for y prime and we'll be done. Okay, I'm kidding, we won't be, but we're getting there. Y prime equals 1 over cosine y. Now we're not going to leave the derivative of y with respect to x in terms of y's. So this is where the big duh of trig comes in. We've got the idea that the sine squared of any angle, I'll use y, plus the cosine squared of any angle, I'll use y, is 1. And now we can really easily solve by subtracting sine squared of our angle and then square rooting. Okay? And now what I have is just a really tremendous substitution for y prime, which I'm being sarcastic actually, because if I were to plug the square root of 1 minus sine squared y in here, it looks worse than this one, and I still have the derivative of y with respect to x in terms of y. But the reason that I did that, and I'll put an asterisk right there, key step. I know that x is sine y, so I know that this could be written as 1 minus, instead of sine squared y, I can do x squared. And that's the substitution that we're going to use in our final step to get our derivative. And this is actually our derivative of our arcsine function. Now remember, we don't always just take the derivative where our inner function is a plain old x. So let's real quick look at what happens if our derivative is something other than a plain old x. Well, we're going to say that the derivative of arcsine u is 1 over the square root of 1 minus u squared. And then we're going to times by the derivative of u. It's that easy. So instead of when we just have a plain old x, 1 over the square root of 1 minus x squared, we just add that little derivative of u in there. Okay, that needs some practice, so let's look at one. All right, now we should never, ever, ever have to go through that whole awful process again. I mean, except for when we do the arctangent next. But in reality, this should be all we need to know about this, and you just remember it, right? We will have to memorize some things in AP Calc. Alrighty, so arcsine x squared, well, let's just use the pattern. It's supposed to be, let's figure out what u is. U is the inner function, so that's going to be our x squared. The derivative of u, u prime, derivative of u with respect to x, is just 2x, right? Derivative of x squared is 2x. And now we're just going to go ahead and plug stuff in. So the derivative would be 1 over the square root of 1 minus u, which is x squared, times u prime, which is 2x. And of course, this could have some simplifying going on. AP exam would probably have this answer down in your multiple choice. Okay, so that's the best answer, but this is the basic pattern for you. Okay, let's move on. Okay, so we've got y equals the arctangent of x, and we want to find y prime. If we already had these memorized, we'd be doing no work right now, just plugging things into a formula, but we don't know yet. So let's go ahead and do the same idea. We're going to change forms. If x is the angle whose y is the angle whose tangent is x, then this must be true. Taking the tangent of y must give us x. And once again, now we're home free. I can take the derivative using implicit differentiation here, just from basic patterns. Derivative of x with respect to x is 1. Derivative of tangent is secant squared, inner function unchanged, times the derivative of the inner function. And now we can go ahead and solve for y prime by dividing by secant squared. And once again, we're going to make a substitution using those ideas from our Pythagorean identities. And we're going to use the one that says has tangent and secant squared in it, because we're trying to get rid of there is that secant squared. And we're just going to make a substitution. Now, it may seem silly, why would we want to put that in? But the deal is this, back to this cool step. When we changed forms, I know that another way to say tangent y is x. So if I want to say tangent squared y, I'm going to put x squared. And that's the substitution that we're going to use down here. And that there is the derivative of arctangent x. If we want to find the derivative of arctangent u, where this inner function is not just a plain old x, it'll look very similar. 1 over u squared plus 1. But then the chain rule tells us we've got to take the derivative of that inner function. All right, let's try one. if we can identify, and this should be all you need to know, if we can identify our inner function, which is root x, and the derivative of our inner function, and you can call that derivative with respect to x, or you could just use the u prime, power function, multiply, drop it down a power, so it'd be x to the negative 1/2. So I'll put that in the denominator as a root x. And now we're basically done. I'm going to just plug stuff in. 1 over u squared. And yes, root x squared is just x, and you can totally do that, times the derivative of u. And you can simplify enough to do whatever to match your answer on an AP exam. On a free response, you only simplify if it's convenient for you. Okay, so hopefully this is getting a little redundant. I'll just run through this one pretty quickly. If we do our changing forms, then we should be able to take the derivative of secant is secant y tangent y times the derivative of the inner function, so y prime when we divide out the gooky stuff. We're going to need some substitutions, and you've probably guessed that it's that secant squared and tangent identity that's really going to help us. So secant squared y equals tangent squared y plus 1. Now, we already know a nice substitution for secant y here, right? I'll put the asterisk again by that step. So we're okay with this. And in your book on page, we're running out of time on my video here, so in your book on page 167, they talk about why we need to use absolute values here for this x. Just take a peek at it. Nothing earth-shattering, just some domain issues. And then we can go ahead and make a substitution here for tangent squared y. We'll subtract 1. Then take the square root. I'm doing this in one step. And then when we make the substitution for x in here, it's the square root of x squared minus 1. And that's going to be our substitution for tangent y. And once again, if we had something with the u in it, we would just have to tag on that u prime. Okay, so let's try one. Identify your inner function and your derivative. And all you do is go and plug it in. Times the derivative of that inner function. And there's certainly some simplifying. The idea that 5x to the 4th is always positive, and that we could put our 20x to the 3rd up here. 5x to the 4th doesn't require absolute values. This could certainly be changed to 25x to the 8th. And you could do some reducing here for a final, probably more matchable answer would be a 4 up here and an x and down here. And that's all I've got for you, folks.